So, welcome to this first session on problem solving for trigonometric and inverse trigonometric functions. So, in the last lecture we finished our discussion on inverse trigonometric functions. We solved a few problems also. In the next two lectures we will be basically solving some problems on both trigonometric and inverse trigonometric functions, and thereafter we will be starting a new topic on properties of triangles. So, this is the first problem. So, most of the problems that we will be discussing in today's lecture and the next lecture will be from JEE exam. So, in this problem it is said that A, B and C are positive numbers, and we are asked to find the value of the sum of the tan inverses of three different values. So, immediately it appears that we should use the tan inverse x plus tan inverse y formula. So, we will start with adding the first two terms, and before that what we see is that all these three values have a plus b plus c as a common factor, and then what we can also do is that we can actually multiply this first one by square root of a both in the numerator and denominator. So, what we are going to get is, so if you multiply both the numerator and the denominator inside the square root with a is going to come out, and we are going to get a into square root of a plus b plus c over abc. So, the first term is this quantity plus tan inverse of, for the second term we are going to multiply this thing by square root of b. So, both the numerator and the denominator. So, we will end up getting the second term as tan inverse of b times square root of a plus b plus c over a b c. And then we intend to use the tan inverse x plus tan inverse y formula, and that is something that we have already covered in the previous one of the previous lectures. So, for the tan inverse x plus tan inverse y formula, so let me just recollect that. So, this value will depend on the signs, the sign of x and sign of y, and also on the value of the product x y. So, to be precise, it is given by equals. So, there are three cases. So, the first case is if the product of x and y is less than 1. So, in that case this is equal to tan inverse of x plus y over 1 minus x y. And then the other cases are when x into y is greater than or equal to 1. So, the other case is x y is greater than or equal to 1, and so even for x y greater than or equal to 1 there are two sub cases. So, when x y is greater than or equal to 1, either both x and y are positive or they are both negative. So, this is the second case. So, if we have this case, then the value is given by, so this expression is still going to remain. So, it will be pi plus tan inverse of x plus y over 1 minus x y. And the third case is when, again when the product x y is greater than or equal to 1, but both x and y are negative, and in that case the expression is minus pi plus tan inverse of x plus y over 1 minus x y. So now we have to in order to use this formula, we have with this. So in this case, we would like to, in our case now, we would like to evaluate this expression. So for us, let's say this is x and this is y, and then we have to first look at the product of x and y. So the product of x and y is a plus b plus c over, this will be over c, because we will get a times b, and then in the denominator we have a b c. So the a b is going to get cancelled, and what remains in the denominator is only c. And this obviously is strictly greater than 1, because it is given that a, b and c are all positive, and therefore for this case, so this is the condition which gets satisfied for us now, because if you see, this is positive because a, b and c are all positive. This is also positive because all a, b and c are positive, plus x into y is strictly greater than 1. So this second case is the one which we qualify for, and therefore tan inverse of a into square root of a plus b plus c over a b c plus tan inverse of b into square root of tan inverse. So tan inverse of a into square root of a plus b plus c over a b c plus tan inverse of b into square root of a plus b plus c over a b c is going to be equal to, so we take this second expression, pi plus tan inverse of x plus y. So x plus y is going to be this plus this, which can be written as a plus b into square root of a plus b plus c over a b c divided by 1 minus x y. X times y is, or we have already seen that it is equal to a plus b plus c over c, and further simplification will give us pi plus tan inverse of. So this denominator is going to become, so after simplification this is going to become minus c into square root of a plus b plus c over a b c. Now we know that the tan inverse function is an odd function, and therefore tan inverse of x, tan inverse of minus x is equal to, so for any x, tan inverse of minus x is equal to minus of tan inverse of x. So this is the result we are going to use here, and then we get this to be equal to pi minus tan inverse of c into square root of a plus b plus c over a b c. And therefore if we take this sum on this side, we exactly get these three terms, because this last term, if you see, this last term is precisely equal to this term, and therefore when we take this term from the right hand side to the left hand side, what we will end up getting is that this entire sum will be equal to pi. So that finishes the first problem. So here is the next problem. So in this problem, for all mod x less than or equal to 1, we are asked to find the smallest and the greatest value of this quantity, which is sin inverse x to the power 4 plus cos inverse x to the power 4. Now we know that sin inverse x has a range which is from minus pi by 2 to plus pi by 2. Cos inverse x belongs to the interval 0 to pi, but we also know the result that for any x such that mod x is less than or equal to 1, we know that sin inverse x plus cos inverse x is pi over 2. So, this is true, and though we have powers of 4 here, we would be interested in using this identity somehow. So, if you want to use that identity, then we can write this expression as equal to sin inverse x to the power 4 plus pi by 2 minus sin inverse x to the power 4. And just to simplify this, let us say that theta is equal to sin inverse x, and of course theta has to belong to the interval minus pi by 2 to plus pi by 2, which is the range set of sin inverse, and then this entire expression becomes in terms of theta, that is equal to theta to the power 4 plus pi minus pi by 2. So, theta to the power 4 plus pi by 2 minus theta to the power 4. So, what we are asked to do is to find the largest and the smallest values. So, let me say that this is f of theta. So, immediately what comes to mind is to take the first derivative of f theta. So, the first derivative of f theta is going to be 4 theta cube minus 4 into pi by 2 minus theta cube. So, this is the first derivative, and to find the extremum points we have to equate this to 0. So, then the equation that we get is theta cube minus pi by 2 minus theta cube equals 0, or in other words theta cube is equal to pi by 2 minus theta cube. Now, since both theta and pi by 2 minus theta are real, so the only solution to this, the only real solution to this particular equation is that theta is equal to pi by 2 minus theta, which implies that there is an extremum point at theta equal to pi over 4. And that because x, so the corresponding value of x is going to be sine of pi by 4, which is 1 over root 2. So, now, but we have to see whether this is a maxima or a minima point, whether it is a maximum or a minimum, for which we have to take the second derivative of this function f theta with respect to theta. So, this second derivative of so the there is one subtle point also here that we must realize is that we are asked to find the maxima minima of this particular function, but we are not asked to find the value of x for which the maxima or minima is obtained. We are just asked to find the value of the function, the maximum or the minimum value of the function as it is. So, that value is going to be the same as the maximum or the minimum value of this function. So, that is why we have made this substitution, and we will only focus our attention on this particular function now. So, now this second derivative will be equal to 12 times theta square plus 12 times pi by 2 minus theta square, which as you can see is greater than 0, and therefore, it is implied that theta equal to pi by 4 is a minimum point. So, it is a minimum for f theta, and the interesting thing is that it does lie. So, this theta equal to pi by 4 does lie in the interval minus pi by 2 to plus pi by 2. So, we are certainly sure that therefore, the minimum value of f theta for theta belonging to minus pi by 2 to plus pi by 2 is, so if you remember, f theta was this function, and so essentially this and this are equal at theta equal to pi by 4. So, the value automatically becomes 2 times pi over 4 to the power of 4, which is pi to the power 4 over. So, 4 to the power 4 is 256. So, it is 128. So, this is the minimum value of this. So, the minimum value of sin inverse x to the power 4 plus cos inverse x to the power 4 is pi to the power 4 over 128. Now, the tricky part is to actually find the maximum value, and we know that there is no maxima of this function, but then since the domain of this function is limited to minus pi by 2 to plus pi by 2, which is a finite interval, finite length interval. So, there has to be a maxima somewhere as long as theta is restricted to this finite interval. So, for that we have to actually try to look at the first derivative and see what is happening. So, if we see that the first derivative was 4 times theta cube minus pi by 2 minus theta cube. Now, it is clear from here that whenever, so since see the value of theta is between minus pi by 2 to plus pi by 2. So, we need to examine the value of the first derivative, or rather plot a graph for f dash theta with respect to theta. We know that there is only one place where it is equal to 0, but what about the value of the first derivative at other values of theta in this interval? So, it is clear that when theta is greater than pi by 2 minus theta, let us consider this region of theta. So, when this is true, that implies that, so when this is true, then well, it actually depends on the values taken by whether it is positive or negative. So, a little graphical plot would actually help us here. So, here we have theta on the horizontal axis, and on the vertical axis we are going to plot theta cube minus pi by 2 minus theta cube, and we have theta, let us say, between minus pi by 2 and plus pi by 2. So, let us say this is our pi by 2. So, this is pi by 4, this is 0, this is minus pi over 4, and this is minus pi over 2. So, we know that this value is exactly equal to 0 at theta equal to pi by 4. So, now let us see what happens when theta is greater than pi by 4, and of course, less than equal to pi by 2, so which is this region. So, when theta is between these two values, then both theta as well as pi by 2 minus theta are positive, and also in this region theta is greater than pi by 2 minus theta, and therefore, this first derivative has to be positive. So, in this region, it is clear that f dash theta is greater than or equal to 0. So, which means that if but because it is cubic, so it will look something like and since it is always positive, so might take some value like this. So, this is our, so this is, let us say this is the curve for f dash theta in this interval, and then let us then look at the other interval which is for, let us say theta is less than or equal to pi over 4, but theta is positive. When theta is satisfying this condition, what we have is that theta will be less than pi by 2 minus theta. So, when theta is in this region, this is true, and therefore, now since both theta is also positive and pi by 2 minus theta is also positive, and theta is less than pi by 2 minus theta for when we are in this region. So, what will happen is that the value of this first derivative is going to be negative, because theta is less than pi by 2 minus theta, and both theta and pi by 2 minus theta are positive. So, therefore, it will be negative, which means that f dash theta will be, let us say, somewhere here, something like that. So, we have f dash theta is negative in this interval, and then similarly we have to consider the other we have to consider negative values of theta. So, when theta is less than or equal to 0, so when theta is negative, what we see is that theta cube is going to be negative. So, when theta is negative, theta cube is also negative, and what we see is that pi by 2 minus theta will be a positive value, and therefore, pi by 2 minus theta cube will be positive, but because there is a negative sign here, minus of pi by 2 minus theta cube is also going to be negative, and therefore, when theta is less than or equal to 0, the first derivative f dash theta is also again going to be negative. So, if I had to plot it further, so let me replot it. Essentially, this graph, this curve would be still negative, like something like this. So, the graph is not exact. What is more important here is whether f dash theta is positive or negative. So, just to summarize the discussion on the previous slide, what we have found out is that when theta is greater than or equal to pi by 4 and less than or equal to pi over 2, we have the first derivative as positive, and when theta is less than or equal to pi by 4 and greater than or equal to minus pi by 2, then the first derivative is negative. And therefore, from this what we actually, if we were to, from this, and of course, we know that at theta equal to pi by 4, the derivative is equal to 0. So, we can approximately plot the graph of f theta. So, we have theta here. So, we have pi by 2 minus pi by 2, and so this is pi by 4, this is minus pi by 4. So what is going to happen is that the minimum value, as we have seen, is pi to the power 4 by 128. So let us say this value here is pi to the power 4 by 128, and that minimum value is attained at pi by 4. Now we know that in this interval f dash theta is positive, and therefore f theta will increase monotonically in this interval. So it might go something like that. And then in this interval from minus pi by 2 to pi by 4, we know that it is negative, which means that it would be decreasing. Starting from here, the value would be decreasing like that. Please note that these are not exact values, these are just indicative values, okay, just to explain you that the function is first decreasing from, and this decrease is monotonic, because in this entire range the derivative, the first derivative is negative. So this decrease is monotonic. So it first decreases monotonically from minus pi by 2 to plus pi by 4, and then from pi by 4 to plus pi by 2 it increases monotonically. So the graph is expected to be something like this. Please note that this is not an exact graph, and also in the previous slide please note that this is not an exact graph, it was just for the sake of illustration. And anyways, what is most important for us in this problem is to know the regions where the derivative is positive and where it is negative. So from this it is clear that the minimum is at pi by 4, but then we see that, clearly see that the maximum of f theta in this interval will be either this value or this value, and therefore we need to calculate these two values and compare them. So essentially what we have to do now is to find the value of f theta, which is theta 4 plus pi by 2 minus theta to the power 4 at both the endpoints. So the value at theta equal to minus pi by 2 will be pi to the power 4 by 16 plus, and this will be pi to the power 4. The value at pi over 2 will be only pi to the power 4 by 16. So obviously this is the larger value, and hence the maximum value of sin inverse x to the power 4 plus cos inverse x to the power 4 is equal to pi 4 by 16 plus pi 4. Well, that is actually pi 4 into 17 by 16. So this is the maximum value, and the minimum value is pi to the power 4 over 128. So this finishes the solution to the second problem. Another very interesting problem is asking us to find the number of solutions to this particular trigonometric equation, but only when x is constrained to lie in the interval minus 2 pi to plus 2 pi. So for such many times we have to use graphical techniques because it's not possible to exactly solve and find the points where this left hand side and right hand side are equal. So this is one such example. So let us so the way we are going to solve this problem is that we are going to actually understand and compute this particular function. So we will start with sine inverse of sine x and see how it looks when x is constrained to this interval here. And that is not very difficult because so let us say that sine inverse of sine x is equal to y. So of course this value of y has to belong to the range set of the sine inverse function, which is minus pi by 2 to plus pi by 2, but we need to express this y in terms of x. That is what our ultimate goal is going to be. So, from here if we apply the sine function on both the sides, then we get sine x is equal to sine of y. So, now we divide this into several regions. So, the first region is when x is, let us say, between minus pi by 2 to plus pi by 2. So, when x is in this interval minus pi by 2 to plus pi by 2, we know that if we restrict to this interval, then sine of x is a monotonic function, and therefore, if sine x is equal to sine y, then it must be true that this y is equal to x, because remember that y already belongs to minus pi by 2 to plus pi by 2. So, if x is in this interval, then sine inverse of sine x is equal to x, and this we have already seen several times in previous lectures. The next interval is x is greater than or equal to pi by 2 and it is less than or equal to 3 pi over 2. So, obviously, when x is in this interval, sine inverse of sine x cannot be equal to x, because sine inverse of sine x has to belong to this interval, whereas x is not belonging to that interval. So, but for this interval what we see is that if x belongs to this interval, then pi minus x is going to belong to the range set of sine inverse, which is this set. And further we know that sine of pi minus x is equal to sine of x, which is already equal to sine of y. So, what we have here is that sine of pi minus x is equal to sine y, and pi, so y is already belonging to minus pi by 2 to plus pi by 2. Pi minus x is also belonging to this interval, and therefore, it must be true that pi minus x is equal to y. So, what is implied from here is that pi minus x is equal to y, which implies that. So, for the second case, which is x greater than or equal to pi by 2 and less than or equal to 3 pi over 2, what we have is that pi minus x is y, which is sine inverse of sine x. Therefore, sine inverse of sine x is pi minus x if x belongs to this interval. Similarly, if x is greater than or equal to 3 pi over 2 less than 5 pi over 2, then again in a similar manner, since well, we know that if x is in this interval, then x minus 2 pi is going to belong to again the range set of sine inverse, and because we are just shifting x by 2 pi, it is clear that sine of x minus 2 pi is equal to sine x, which is sine y. So, here what we have is sine of x minus 2 pi is sine y, and both x minus 2 pi and y belong to the range set of sine inverse, which is minus pi by 2 to plus pi by 2, and therefore, it must be true that y is equal to x minus 2 pi. And a similar kind of argument can be done for the negative x, and after all this effort, what we are going to get is that, so for x between minus 5 pi by 2 and plus 5 pi by 2, this is how sine inverse of sine x is going to look. And then we plot this exactly on, so here we plot, so we have 3 different curves in the same plot. So, the horizontal axis is representing x, and we have to limit ourselves to the interval minus 2 pi to plus 2 pi, and that is because it was asked in the question that how many solutions are there to this equation for x restricted to this interval. So, in the blue curve here is for sine inverse of sine x. So, that is the blue curve here, and then mod of sine inverse sine x has been plotted with a dotted line shown in red, and that is very easy to plot because whenever the blue line is on the positive upper half, the red line is going to be exactly the same, but when the blue line is on the negative half, then the red line is just going to be a mirror image about the x axis. So, that is how we get mod of sine inverse sine x. And then since we had to find the number of solutions to, or number of distinct different points x such that mod of sine inverse sine x is equal to cos x. So, we have to also plot graph for cos x. So, in black, so this black curve here is for cos of x, and it is very clear that so now what we have to ultimately find out is the places where the red dotted curve and the blue and the black curve are intersecting. So, the first place is over here, and then the second place is here, and then immediately we get another point over here, and then we get the last point over here. So, we do not go beyond 2 pi and minus 2 pi, because we have to restrict ourselves to minus 2 pi to plus 2 pi. So, we see that there are 4 distinct solutions where both these curves will meet, and therefore, the number of solutions to the equation mod of sine inverse sine x equal to cos x is 4. So, that solves the third problem also. So, what we see is that many times we have to take use of graphical methods also. So, that is one take from this particular question. So, here is another interesting problem, and this is also a problem from one of the previous JEE exams. So, it says that let S be this set. So, we are essentially restricting our x to the open interval minus pi to plus pi, and the x is not allowed to take the value 0 and plus pi by 2 and minus pi by 2. And then what we have here is a trigonometric equation, and we are asked to find the sum of all the distinct solutions to this trigonometric equations. So, obviously, we have to first solve this trigonometric equation and then take the sum of all the distinct solutions. So, the word distinct is also very important, because sometimes we might get double roots, and so basically 2 values of the same x. So, starting we basically have that root 3 secant x plus cosecant x plus 2 times. So, this is the trigonometric equation, and this of course is root 3 over cos x plus 1 over sin x plus 2 times sin x by cos x minus cos x by sin x equal to 0. Now, since it was mentioned that x cannot be plus minus pi by 2 and also not 0, and x can also not be equal to plus or minus pi. So, since x cannot be 0 and neither can it be plus minus pi, so it is clear that for all x belonging to S, sin x is not equal to 0. Similarly, since x is not equal to plus minus pi by 2, for all x belonging to this set S, cos x is also not equal to 0, and hence their product is also not equal to 0. So, we know that if x belongs to, for all if x belongs to S, then sin x times cos x is not 0, and therefore, now if we multiply both the sides of this equation with sin x cos x, what we end up getting is that root 3 sin x plus cos x plus 2 times sine square x minus cos square x equals 0, and a little bit of rearranging these terms is going to give us root 3 by 2 sin x plus half cos x is equal to, so this we take it to the right hand side, it becomes cos square x minus sin square x, and we know that cos square x minus sin square x is cos of 2x, and this appears to be of the form cos a cos b plus sin a sin b. So this we can write as cos x into cos pi by 3 plus sin x into sin pi by 3 equals cos of 2x, but cos a cos b plus sin a sin b is cos a minus b, and hence what we get is cos of x minus pi over 3 is equal to cos of 2x. So x will satisfy this equation if and only if it satisfies this equation, as long as x is restricted to the interval S. Taking this forward, and here we are going to essentially use something that we have already seen when we were discussing trigonometric equations. So if you remember, we said that if cos x is equal to cos y, then it must be true that x is equal to y, so sorry, x is equal to 2n pi plus minus y for some integer n. So this is from one of our previous lectures, and what we have here is that cos of x minus pi by 3 is equal to cos of 2x. So essentially what it means is that this 2x must be equal to, I mean we can write it either way, so we can even write it like this. So this is what must be true. So essentially what we are doing here is we are using this equation, and we are taking this as our y in this equation, and this is we are taking it as this x. So if we use this identity, then this is what we end up getting, that if cos of x minus pi by 3 is equal to cos of 2x, then it must be true that 2x is equal to 2n pi plus minus x minus pi by 3. But here n should be an integer. So if we start first with the plus sign here, what we get is 2x must be 2n pi plus x minus pi over 3, which implies that x must be of the form 2n pi minus pi over 3. But remember that we are only allowed the value of x, x must belong only to the interval minus pi to plus pi, and therefore all values of n might not be permissible. So if we take n equal to 0, then the value of x that we get is minus pi by 3, which definitely belongs to the interval minus pi to plus pi. But if we take any other value of n, any other integer value like 1, then the value of x that we get with n equal to 1 is 2 pi minus pi by 3, and this value is definitely not in the interval. So this does not belong to the interval minus pi to plus pi. So this is not a valid solution for us. And the same thing will happen if we take any other integer multiple of which is not 0. So with the plus sign here, the only solution that we get is x equal to minus pi by 3. Now let us see what we get with the negative sign here. So that equation is 2x must be equal to 2n pi minus x minus pi by 3, and that can then be written as 3x is equal to 2n pi plus pi over 3, or x is equal to 2n pi over 3 plus pi over 9. Again, starting with n equal to 0, we get x equal to pi over 9, which of course belongs to the interval minus pi to plus pi. With n equal to 1, we get x equal to 2 pi by 3 plus pi by 9. So this is also a valid solution for us, because this also belongs to the interval minus pi to plus pi. But if we take larger values of n, like n equal to 2 and so on, then the value that we get will not belong to minus pi to plus pi, and therefore those are not valid solutions for us. On the negative side, if we take n equal to minus 1, then we get x equal to minus 2 pi over 3 plus pi by 9, and this value of course belongs to the interval minus pi to, so minus pi to plus pi. But if we take n equal to minus 2, then that value will not belong to the interval minus pi to plus pi. So that solution is not allowed. So with the negative sign here, we get 3 valid solutions, and with the positive sign, we only got one solution, which was x equal to minus pi by 3. So that is the fourth solution. So totally we get 4 different valid solutions of x for that for this trigonometric equation. And then we were, if you remember, we were actually asked to find the sum of all the distinct solutions. So as we can see, all of these solutions are actually distinct. So none of them is equal to the other. And when we take their sum, what we get is, so of course this and this will cancel, and when you add this and this and this, we will get pi by 3, but that when added to this will give us 0. So it turns out that the sum of all these 4 distinct values is in fact equal to 0. So the final answer is that the sum of all the distinct solutions to this equation, where the solutions belong to the set S, is equal to 0. If we go back a few steps back, then we started with cos of 2x equal to cos of x minus pi over 3. And we said that the general solution to this equation is of the form that 2x must be equal to 2n pi plus minus x minus pi by 3. Now, some student might wonder that since cos is an even function, cos of x minus pi by 3 is actually also equal to cos of pi by 3 minus x. So, but if we start with cos of 2x equal to cos of pi by 3 minus x, and then solve it exactly in the manner we did, are we going to get the same set of solutions? And the answer to that question is of course yes. And that is because if we, let's say, start with this equation, so instead of x minus pi by 3, we have pi by 3 minus x. So again the same, because the general solution to this equation will also be of the form 2n pi plus minus pi by 3 minus x. But if we see this, the important thing here to see is this plus minus. So because we have a plus here, so with the plus, what we will get is 2n pi plus x minus pi by 3. When we take the minus, we get 2n pi minus x minus pi by 3. But which is actually, so when we take the minus sign here, that is, the expression is exactly equal to what we get in this case with the plus sign. And similarly, what we get here with the minus sign is exactly equal to what we get here with the plus sign. So that is why both the things are going to be same. They are going to give us the same solution. So with that, we'll end this lecture, and in the next lecture, we'll do some more similar problems. Thank you.